Hello, this and my other YouTube videos are extracted from the History of Man series, currently 6 books published in print, ebook, and most importantly, audiobook. I'm a storyteller, and if you like these video stories, you'll love the History of Man series audiobooks. Great for commuting, or just sitting back and relaxing. And unlike a novel you've read where you know the ending, you can listen to these books on tape more than once. There's so much to learn. Available on Amazon and audible.com, I narrate the audiobooks. And the best part about that is you can listen to these stories without having to look at my stupid face. And with that said, let's get the show on the road. Hello, I'm John Bershoff with another episode of History of Man series. Today's subject, waves, Doppler effect, and the age of the universe. And I apologize in advance, it's a long video. I don't like long videos, but there's a lot to cover here, so let's just truck on. The Doppler effect is used or was discovered to determine how fast and in what direction a star is moving away from us or toward us on Earth. Now, when a wave is traveling toward an observer, it's true for sound and it's true for light. The waves pile up on each other, they overlap, they become compressed because the source has speed, has velocity, the observer does not. The waves become shorter. When a wave is traveling away from the observer, they are free to elongate. Again, because the source has speed, is moving away, has velocity, the waves become longer. Now imagine for a moment you're standing alongside the Pacific Coast Highway in California. Beautiful highway, coursing along the Pacific Ocean through such idyllic communities as Half Moon Bay, Carmel by the Sea, Monterey, Big Sur, San Simeon. A Pontiac GTO, a muscle car out of Detroit, is coming towards you. The sound the car makes, the sound the GTO makes is high pitched. Waves compress. Eee! As the GTO passes you and speeds down the road, the sound waves are elongated to a lower pitch. Eee! Same is true of light waves. Light traveling towards the observer compresses into the blue spectrum. Light traveling away from the observer elongates into the red spectrum. Our story begins with Austrian physicist Christian Doppler, born in Salzburg in 1803. He noticed that certain binary stars, which are two stars rotating around each other, two stars together, he observed that the frequency of the light wave that he was observing relative to him had elongated, had gone into the red spectrum. It appeared to Doppler that these stars, red shifting, were moving away from him, away from Earth, from the observer. Now, changing gears for a moment, ultrasound is sound frequency above human hearing, above 2 megahertz. Diagnostic ultrasound in medicine varies between 2 and 18 megahertz. How does ultrasound, or even sound for that matter, vary according to the material it is bouncing off of? An example, just talk with your face inches away from a wood wall and then a brick wall. Sounds different because wood versus brick bounces sound waves differently. But don't let anyone catch you talking to a wall, or you'll end up in the loony bin talking to a psychiatrist smoking a pipe. Now, diagnostic ultrasound in medicine are waves, sound waves produced by the transducer that change and bounce back according to the varying tissues they encounter in the body: skin, fat, muscle, tendon, bone. And as they bounce back, a receiver receives those changes in frequency and images them onto a screen with the help of a computer, of course. You can ultrasound a fetus inside the womb, a breast mass, abdominal mass, pelvic mass, really any mass, except a religious mass. Now, classic x-rays, like a chest x-ray, are different than ultrasound waves. They don't bounce, they pass through. They are usually high-energy electrons or radiation that passes through things differentially, depending on what they're passing through, to the other side, to the dark side, where they're imaged. Difference between ultrasound and x-rays. But returning to sound waves, a Doppler ultrasound is an ultrasound with a Doppler attachment because certain things inside the body move, like a fetus inside the womb or blood in the carotid artery. Big red is carotid, big blue is jugular, in case you were wondering. And the change in frequency of movement towards or away from the receiver is shown as a waveform converted by a computer to real time. So you can see blood flow through the carotid artery to see if big red is blocked. Now, continuing with our Doppler discussion, into our story steps Edwin Hubble, born in 1889 in Marshfield, Missouri. At one high school track meet in 1906, age 17, he won 7 first-place medals. 7. He's quite the athlete. He then went on to study math and astronomy at the University of Chicago. Math and astronomy, his true love. But he detoured to Oxford to study law per his father's wishes. But when his father died in 1913, Hubble dropped law like you and I might drop fifth period literature and turned his gaze to the stars. In 1919, age 30, Hubble ventured to Mount Wilson Observatory in California, which housed the largest telescope in the world at the time, the 100-inch Hooker telescope. Not Hooker because the funds came from a hooker. Well, they sort of did. They came from John Hooker, a wealthy businessman in iron and steel fabrication and an amateur astronomer who paid for the telescope. Now, scientists from antiquity, Aristotle, Ptolemy, Eratosthenes, had Earth at the center of the universe. The church liked that and made sure it was true, although it was really dogma. 1,500 years later or so, guys like Copernicus, Kepler, and Galileo in the 16th century had the sun at the center of the universe. Heresy in the eyes of the church, such thoughts could get you burned at the stake. Now, the Milky Way was known since antiquity. You look up in the sky and you can see it. But what it was left to the imagination. Little did stargazers know from antiquity, at least up until the 19th century, that the Milky Way they were looking at was our galaxy, which is why our galaxy is called the Milky Way. Now, into our story steps Edmund Halley of Halley's Comet fame. In 1718, Halley, using star positions from Ptolemy in the 2nd century AD, compared to his measurements, proved stars were moving, that they had moved a little bit since Ptolemy's time. They were not fixed in the night sky as Ptolemy had described, like everyone thought. By the way, Halley did not discover Halley's comet. He merely demonstrated it was a recurring comet every 75 to 79 years, so it was named after him. Now, in the next century, in the 1800s, several astronomers using what are called parallax measurements. Parallax measurements are measurements, let's say, of a star from 2 points, like if you're on Earth, like opposite seasons, the spring equinox and the fall equinox. Not easy when you're stuck on Earth. But these parallax measurements of a single star from 2 different points seem to point that our solar system, our sun and Earth, was not much the center of anything. These parallax measurements proved that our solar system was within the Milky Way, but where it was not at the center of the Milky Way galaxy. It was on some remote arm that is now called the Orion arm of the Milky Way. Earth and sun was no longer the center of anything. Now, in 1842, returning to Christian Doppler, he demonstrated that light from those binary star systems had redshifted. That means they were moving away from him, away from us, away from Earth. In the 1920s, a guy named Heber Curtis suggested that our Milky Way was not the only galaxy in the universe. That he speculated there were other galaxies. But it was Hubble. From 1923 to 1929, Edwin Hubble demonstrated that not only was the Milky Way not the only galaxy, that not only what were thought to be binary star systems were in fact other galaxies, each with billions and billions of stars, but that most galaxies were moving away from us, away from Hubble, sitting at the Hooker telescope. Hubble proved those stars, those galaxies were redshifting according to the Doppler effect. The universe was expanding and actually picking up speed. Now, by the numbers, there are 2 trillion galaxies in the observable universe. There are 100 million stars on average in each galaxy. That means there are perhaps 1 septillion stars in the universe. That's a 1 followed by 24 zeros. That's a big number. Now imagine how many planets there are orbiting those stars, those suns. How many planets might be in the habitable zone? How many of those habitable zone planets have life? How many of those with life have intelligent life? Because by God, sometimes it does not appear that there's much intelligent life on our puny earth. But anyway, it is called the Drake equation, 1961, the brainchild of Frank Drake, that initially applied to our Milky Way, but it probably can be applied to the entire universe. It is, simply stated, ever-increasing fractions or odds of finding life. The average rate of star formation in our galaxy, the fraction of those stars that have planets, the average number of planets that can potentially support life that are existing in the habitable zone, the fraction of planets that could support life that actually develop life at some point, the fraction of planets that life actually develops goes on to develop intelligent life or civilization, the fraction of civilizations that develop technology that release detectable signs of their existence into space, and then the length of time for such civilizations to actually release detectable signals into space that we might pick up on Earth. According to the Drake equation, from the Milky Way alone, there are 12,500 intelligent alien species. As far as applying the Drake equation to the universe, well, that would be a big number. Now, as for the age of the universe, I need to bring in a grease board because we need to look at some equations. I don't like equations either, but it's the only way I can understand stuff. Sir Isaac Newton steps into our story to help us determine the age of the universe, which needs Hubble's constant. I think guys like Newton, Einstein were aliens, actually. But Newton gave us, besides calculus and gravity, he gave us the laws of motion, including velocity, which equals distance traveled divided by time it takes to get there. Or Newton gave us velocity equals d over t. Now we'll be using that in a moment. Using Dopplers, how far a distant galaxy has redshifted gives us a percentage of the speed of light, gives us the velocity or v. That is, if it's redshifting, the further it redshifts, you can use that percentage of redshifting to determine how fast that star is moving away from us compared to the speed of light. It gives us, in Newton's equation, Doppler redshift gives us v, the percent of light, which is also Hubble's constant. Now, distance d is a little more difficult to understand. We use what are called standard candles, currently called parsecs. But before parsecs, astronomers used stars for distances like Alpha Centauri, the closest star to us, or Sirius, but it didn't have much meaning. It was not terribly accurate or meaningful. Using the distance light travels in a year, a light year, which is a measurement of distance, not time, had problems too, the least of which was accuracy of distant stars. I mean, how do you know for sure that a distant star that took that long for the light to get to us. So the parsec was born. It comes from the distance a theoretical star from Earth would make as measured or would form a single arc second, or 1/3600th of a circle. Now, the Babylonians gave us the clock. 1 hour, there's 60 minutes and 60 seconds, and those seconds are 1/3600th. And the reason the Babylonians selected 360 degrees for a circle is it's such a compacted number. 1, 2, 5, 10, 15, 20, 30, all kinds of numbers go into 360, which is why they chose 360 for a circle, and for seconds, it's 1/360th of a second. But what astronomers wanted to do is use that 1 arc second. Now, this angle's drawn too wide open. It should be much more narrower, but of course I couldn't draw it that narrow. But if you do a 1 arc second of an angle and measure this distance to a theoretical star, that gives you 1 parsec. This star doesn't exist. It's actually, this theoretical star is actually closer to us than Alpha Centauri, which is the closest star to us. But 1 parsec, or 1 arc second, this measurement here is 3.26 light years, or 20 quadrillion miles. But more importantly, it's a standard candle. It is used to measure stars further and further away by determining the angle, okay? Now, so you can create a ladder of parsecs of standard candles using the parsec. But as for the age of the universe, what good does that do? Well, into our story steps Cepheid variables. Cepheid variables are stars that actually pulsate. They have the exact same pulsation no matter where they are in the universe. They're a particular type of star that pulsates. But of course, the further a Cepheid variable is from Earth, the longer the time is between those pulsations. So it helps you determine how many parsecs or megaparsecs that star, that Cepheid variable is from us. So to find the age of the universe, what astronomers did is they went to some galaxy or some area of the universe and they found a number of Cepheids pulsating. So they have more than one data point, and they determined how many megaparsecs that stars or those Cepheid variables were from us. They then looked at the red shifting of those same stars or stars near them to get your V. So the Cepheid variables give us D, distance, and then we get the red shifting gives us V. You rearrange the equation where you take Newton's velocity equals distance over time, and you want to solve for time, the age of the universe. So you change the equation, and you have distance in megaparsecs over velocity, which is Hubble's constant, and it gives you an age of the universe of 13.8 billion years. Now, Hubble's constant, the speed at which stars are moving away from us, is believed to be about 73.8 kilometers per second per megaparsec. It's a number that right now suggests how fast the universe is expanding. But using the Doppler redshift, using Cepheid variables to determine the distance, and then the red shifting of those Cepheid variables give us time equals distance over velocity, which is 13.8 billion years. Sorry, this is a long video, some cool stuff to understand. My books, which is, this is the first history of man. I have 6 of them written, I'm writing more. It's a style of writing called jumping off. I start with medicine and science, and I jump off into other stories and then come back to the main subject. It's a style of writing that's not for everybody. I go into history and philosophy and things like music and art and sports, and I always come back to the subject and continue on. Anyway, I hope you enjoyed this. The universe is about 13.8 billion years old, slightly older than Keith Richards. These books, by the way, are available in print, Kindle, and audiobook, and I do the narrating on the audiobook. I hope you enjoyed this rather long video. Sorry, I apologize. I hope you're well and have a good day. Thank you.